New York Times, Mr. Walter Sullivan.
If you can't hear me, please raise your hand. You know, giving a talk beginning at 10 o'clock at night after a large meal and a certain amount of celebration before dinner has its built-in hazards. And I am reminded of a friend of mine who told what must have been an apocryphal story, but still a rather nice one. He lived in upstate Connecticut, and there was one farmer still in town who had a horse and buggy. And my friend was in the bar, so he said, and they heard this clop, 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 clop outside, and in came the farmer with his bucket and asked the bartender if he had any Beefeater's gin. The bartender said, "You mean that fancy English gin?" He said, "Well, I may be able to find a bottle somewhere." So he dug around under the bar and pulled out this old dusty bottle. The farmer said, "Pour it in the bucket." So he poured it in the bucket, and the farmer looked and said, "That's not enough. Give me another bottle." This guy ain't got another bottle. "I'll give you a bottle of Gilbey's." So he poured that in the bucket. And then the farmer said, "Now give me a tumbler of Noilly Pratt vermouth." So he poured that in the bucket, asked the bartender to fill it with ice, and went out the door, shaking the bucket as he went out the door. Of course, everybody in the bar ran to the window to see what was going to happen. And there was this old nag, its chin down on the ground, and the farmer put the bucket under the horse's nose, and the poor horse went. Pretty soon it was up there with its ears all raring to go, and the farmer came back in with the bucket, and he said, "How much do I owe you?" Everybody was silent for a minute. The bartender said, "Mister, I've never seen nothing like that." He said, "Have a martini on the house." The farmer said, "Are you kidding? I have to drive." In this particular case, I have to talk. But I think that the subject that we're going to discuss is, of course, as Frank said to you, I have found it so utterly fascinating that I hope we'll muddle through somehow in spite of the late hour. What has happened, of course, in the past 10 years is that the Locke hoax type of thing has suddenly become scientifically respectable, scientifically plausible. And what I'd like to do this evening is to reconstruct the steps that culminated, for example, a year ago, last fall, when I was at the Burekhan Observatory in Soviet Armenia, and a very remarkable scientific conference was held there with a number of Nobel laureates from England, the United States, leading astronomers from the Soviet Union, the United States, and France, and other countries. The meeting was organized jointly by the Soviet Academy of Sciences and the National Academy of Sciences in Washington. Nothing could be more respectable, and yet the subject was the subject of our consideration this evening, the possibility of communicating with extraterrestrial civilizations. And what I would like to do this evening is to explain why, at this point, I'm not going to say at this point in time, for heaven's sakes, but at this stage, the scientific community has come to think that this is at least a plausible argument. What made it seem implausible until a decade or two ago was our concept of how the solar system came into being. This is what most made it seem implausible, because it appeared that there probably were no other planetary systems like our own, or if there were any, they were so extraordinarily rare that it would be very unlikely that life would have appeared anywhere, that there would ever be any worlds like our own. And the reason was that what seemed to have formed the solar system was an event that one would not expect to happen ever anywhere else, namely that another star came close enough to our sun so that the gravity of each object working on the other drew material out, the other star drawing material from our sun drawing material from the other star to produce the inner terrestrial planets, the Earth, Mars, Venus, and Mercury, and the material drawn out from the other star forming the distinctly different, lighter, bigger outer planets, Jupiter, Saturn, and so forth. Indeed, the sharp difference in the composition of these two groups of planets is still somewhat puzzling. But the model that we have And that would be an extremely rare event because of the extreme thinness of the distribution of stars even within the Milky Way star system of which we are members. You can imagine, for example, that if we squeezed the whole solar system so that it was in this auditorium, the sun would be perhaps an orange here in the middle. Pluto would be out there in the corners somewhere, and the nearest star, like this orange here, would be another orange or grapefruit or lemon about 100 miles away. With that thinness of distribution, obviously, close encounters would be extremely rare. They would, in effect, never occur. But the new model, the one that seems definitely established now for the formation of the solar system, is the nebular one, which I think many are familiar, that the sun and the planets formed out of a rotating cloud of dust and gas that was pulled together by its own gravity to form a great big blob in the middle whose weight, pressure, and temperature at the core were enough to light off the thermonuclear fires, which became our sun, and the little bits of leftover stuff that condensed to form planets, rather strikingly spaced in a systematic way so that the spacing between at least the inner orbits doubles as you go out. And the little moons, the little family of moons around each of the great outer planets, Saturn and Jupiter at least, formed in very much the same way. We see evidence as we look out into the galaxy in other dust clouds of similar processes taking place today. So that it seems reasonable to hypothesize that planetary systems are a rather common, perhaps universal, but certainly occasional byproduct of star formation. Since there are, by current estimates, about 200 billion stars in the Milky Way system, which you can believe if you go out on deck, not tonight, but on a nice clear night, and look up there at the Milky Way, you realize that it's formed of great clouds of stars, that there are 200 billion stars, 200 billion suns, perhaps even 200 billion planetary systems in this galaxy alone. And of course, in effect, for every one of those stars, if you have a big enough telescope, you can look beyond and see another galaxy, each with its billions of stars. But to persuade ourselves that planetary systems are common, we would like something a little stronger than that in the way of evidence, and we have it. We cannot see planets going in orbit around other stars. We really don't have much hope of doing so. Within the atmosphere, that is, on the surface of the Earth, the light from a star is so scattered that the image in the telescope is bigger than the solar system would be if we were looking at such a system. It's even scattered to a considerable extent just by the optics of the telescope. So even if we had a powerful enough detector to pick up the very, very faint light reflected from the planets, as opposed, of course, to the bright light emitted by the star itself, it would be a very difficult thing to detect. However, there is one way in which we can infer the presence of a planet. And that's the effect that the planet has through its gravitational pull on the star itself. And we can see an example of this in something familiar to any student of astronomy, namely the fact that the path of the Earth around the Sun is not a nice, smooth ellipse, even though it always shows that way in the books. It's not a smooth ellipse, it's a wiggly ellipse. And the reason that it's a wiggly ellipse, of course, is that the Earth has a companion. And this companion, unlike the other 30 or so moons of the solar system, which are tiny dots compared to their parent body, our moon is a very odd moon. It's not like those other moons. It's very substantial compared to its parent body. It has about a quarter the radius of the Earth. And so it's a big hunk of rock with a big gravitational field, not strong as that of the Earth, but nevertheless strong enough so that when the moon is over on this side of the Earth, it's pulling the Earth this way in its path around the Sun. And when the moon gets over here, it pulls the Earth this way, so that each month the Earth wiggles a little bit in its path around the Sun. And this, of course, is the effect that's been seen in some of the nearby stars. You can liken it to a big fat man doing a Viennese waltz with a skinny girl. Now that great big brute of a fellow, he goes around, swinging around the floor, thinking he has complete control over the thing, but he's holding on to this little slip of a girl who's not all that skinny. She still has some weight, and she's pulling on him too, and she perturbs his motion around the floor, and so he wiggles, so to speak, in his moving motion around the floor. Well, this is what they have seen first and foremost in Barnard's star. As we look out at the sky, the nearest single star in the heavens that we can see, not with the naked eye because it's very small, but with telescopes, is Barnard's star. And it being the closest of the individual stars, and that's what we're interested in. We're not really interested in Alpha Centaurus so much because it's in a three-star system. And in that kind of a system, the orbits of planets become extremely complicated. They tend to be in a very hot environment one time, in a very cold environment another time. It's a very unstable kind of situation environmentally, and it's not a very likely place where life would evolve. You want a single star, and Barnard's is the nearest. And it displays what we call proper motion, which simply means that it moves against the backdrop of very distant stars, as do all the nearby stars. In fact, this phenomenon of proper motion is an index of how near, a rough index of how near a star is. As you look out there at an airplane, if the airplane is moving fast in angular velocity, you know it's fairly close. If it's moving very slowly, you know it's way, way out there. And this is the same effect with proper motion. Well, Barnard's star is the sprinter of the sky. In the course of a century, it moves roughly the width of the moon. But the people at Swarthmore, who have specialized in this kind of work, have dug out as many photographic plates of that part of the sky going back to early in the century as they could find. I think it's about 2,100, something like that, plates that have been taken of that part of the sky. And from these they have reconstructed the motion of Barnard's star across the backdrop of very distant objects, and it does not move in a straight line, it wiggles. Now originally they deduced that this was indicated one large Jupiter-like Jovian-type planet in orbit around this small star, almost making it like a two-star system because the star itself is very small. But they've now refined their observations, extended the observations and the calculations, and they realized that it's a multi-planetary system, a rather complicated thing to figure out. But Barnard's star has a family of planets, and they've seen the same effect with some other nearby stars. And it seems very likely that a considerable percentage of the stars in the Milky Way system have planets. Von Kerner at Green Bank, National Radio Astronomy Observatory in Green Bank, West Virginia, has estimated that there are probably, perhaps 200 million planets like the Earth within the Milky Way system. Now, when we say like the Earth, however, we have to remember how lucky we are on this planet in terms of our world having all of these factors that are so important for the appearance of life. First and foremost, we're the right distance from our parent star. We have liquid water. We have a temperate climate. Venus which is the first planet inside the Earth, is too hot, and Mars, the first one outside, is out there on the fringes, very, very cold, and perhaps the middle of life. But there's a sort of a circular argument as far as Venus is concerned, because one of the things that makes Venus so hot is its enormously heavy, massive carbon dioxide atmosphere. The surface pressure on Venus is something like 100 to 150 times that on the Earth because of this enormous blanket of CO2, of carbon dioxide. Now, all of the atmospheres of the inner planets have come out of those planets. There's incontrovertible evidence that early in the solar system's history, presumably heat from the sun drove off, or outrushing gas from the sun drove off all the atmospheres that might have existed around the planets, the inner planets, and all of the air and water on Earth, including this great ocean that we are crossing now, have come out of the volcanoes in the form of steam or through the decay of rocks and so forth. But it's all come from within the Earth. And since Venus and the Earth are twins, are almost identical in size, it's reasonable to suppose that the Venusian volcanoes are more or less like the Earth's volcanoes. So why does Venus have so much CO2? Well, one reason we don't have a great deal of CO2 is because we have life. And having life, having plants that burn up CO2, turn it into carbohydrates, this stows away the CO2 in the ground, in the sedimentary rocks, and in the oil, and in the gas, and so forth, as the planet evolves. Had there been no plants, it's been calculated that our atmosphere would be very much like that of Venus. So we can thank our plant life for the habitability of the world, but there have also been earnest warnings that if we allow the CO2 level of the atmosphere through burning of fossil fuels to get too high, we might get a runaway greenhouse effect that would turn us into a planet like Venus, whose surface temperature is 800 degrees. I don't think even the air conditioning of this ship could cope with that. Well, the greenhouse effect, as you remember, many of you, is what you have in a greenhouse, whereas the glass of a greenhouse permits the visible sunlight to get through, but does not permit the re-radiated energy, the infrared radiation from the heated surface to escape. So CO2 in the atmosphere has a very similar effect, and this builds up the surface temperature. So the Earth does not have this. Mars is frigid, but also Mars has practically a very, very thin atmosphere. And the reason for that is essentially because Mars is just a bit too small. Mars is small enough so that its surface gravity is about a third that of the surface of the Earth, and Mars has great difficulty holding on to oxygen. Now the Earth is just right. If it was bigger, it would hold on to its hydrogen, and we would still have a hydrogen-dominated atmosphere, and the higher forms of life would never have arisen. But the Earth is just right. It's small enough, has a weak enough gravity, so the hydrogen can escape. Hydrogen formed, for example, when water vapor gets in the upper atmosphere and it's dissociated by light from the sun. The hydrogen can escape, but the oxygen cannot. Therefore, we can build up our oxygen level. Mars is not strong enough gravitationally to hold on to its oxygen, so it has a very miserable atmosphere. Its water vapor is depleted because the water gets broken down into hydrogen and oxygen, and they both escape into space. So you have a carbon dioxide dominated atmosphere on Mars, very little water, a very thin atmosphere in any case, and very little free oxygen. Not a very nice place to live. The other requirement is to have a star that has a reasonable lifetime. Again, we're lucky. We have a nice middle-aged star as our parent. The sun is about 4.75 billion years old. It has a nice life expectancy as a hydrogen-burning star, which is what it is now, perhaps 6 billion years more. That will convert to the helium cycle. It will become a red giant. It will go do some horrible things to the planets, vaporizing any life on their surface. But that's quite a ways off. And this is given life time on the Earth to evolve. There is this story, you know, of the lecture at the Royal Astronomical Society in London, that happened to me yesterday, in which the speaker was going through this account of the life cycle of the sun, its eventual turning into a red giant, and somebody in the back of the auditorium broke in and said, "Oh, Mesa, when did you say the solar system was to be vaporized?" And the speaker said, "In 6 billion years." The man said, "Oh, thank God, I thought you said 5 billion years." But anyway, you want a star that has a long life. The M stars, the very small ones, burn very slowly, will have an extremely long lifetime, much longer than that of our sun, but they are so weak in their energy production, that the habitable zone around them is very thin. It's like a small bonfire in the field with a whole lot of people trying to keep warm, and the little zone around that fire that's comfortable is very narrow. Whereas if you have a great big bonfire, a great big star, it'll have a very deep habitable zone around it, but its lifetime is very short, only a few 100 million years probably, and this is not long enough, of course, for life to evolve to anything like its present level on Earth. So we're very lucky in this planet on which we live. But then we are confronted with the biggest question of all. Given a certain number of planets like the Earth in all these respects, on how many of them will life arise? And it's an interesting thing to me that until a century ago, just a few years more than a century ago, the dominant concept was that life arose spontaneously every day here on Earth, and there was no difficulty for people to consider that life would arise spontaneously given the right conditions. Because when people walked through the woods and picked an old log, they'd find maggots in the old log, and it was logical to assume that the wood, after it died, reconstituted itself into maggots. Or the housewife in her kitchen. No Frigidaires in those days. She'd leave the meat around too long, and white worms would appear in the meat. Of course, the molecules of the meat, after the cow died, decided they'd like to be worms, and so they rearranged themselves and became little white worms. And it wasn't until, the first blow that was struck at this idea of spontaneous generation was by the house physician of the Medici family in Florence, who conducted one of the early biological experiments, a real controlled biological experiment. He took 7 vessels, glass vessels, and put 7 pieces of meat in those vessels. He put cheesecloth over some of them, but not over others. And the flies in Florence in those days were formidable. They swarmed all over, but they couldn't get at the meat that had the cheesecloth over the bottle. Well, of course, after a week or so, only the meat that was exposed to direct contact with the flies produced the white worms. And so Reddy demonstrated what he suspected, which was that the flies were laying eggs in the meat, which then hatched into white worms. And yet this idea of spontaneous generation hung on. One of the great contributors to the science of physiology, some consider him the father of physiology, was a Belgian named von Helmont. And von Helmont in the 17th century did a number of experiments which led him to believe that higher animals could be generated from in a spontaneous manner, and instead of being known to the scientific world primarily as the father of physiology, the poor man is known for his recipe for mice. His recipe for mice, and I have it verbatim down in the book, his recipe for mice was that you take an undershirt that's been worn about 2 weeks without being laundered, and place it in a glass vessel with kernels of wheat. You then take the vessel and place it in a dark corner for 21 days. During those 21 days, the fumes from this smelly shirt work on the life force in the kernels of wheat, and the kernels of wheat turn into mice. Now, he did this a number of times. He got mice every time. The biologists today would say it was not properly controlled experiment. But nevertheless, this was obviously was laughed out of court fairly early in the game. But when the microscope came along and they discovered bacteria, they really did seem to arise spontaneously. And that was the last battleground that was fought out just a little over 100 years ago with, of course, Louis Pasteur as the victor. And that is, I find, a fascinating story, because Pasteur was a fantastically meticulous experimenter. And the debate he had was with the head of the Natural History Museum in Rouen, Félix Pouchet, whom everybody, of course, has forgotten now. But he was the standard bearer of the spontaneous generation argument. And he had most of the scientific community behind him. Pasteur, to try to prove his point, took about 20 or 30 glass vessels with goosenecks that could be sealed by simply heating the glass so it fused together. And he filled these with a broth that would be an ideal medium for culturing bacteria. Then he sealed them all with a little flame and boiled them till he was sure every bacterium in there had been killed. He then went down to his childhood home near the Jura Mountains, and he went out into a field, and here's where he showed what a meticulous man he was. He held these flasks one by one over his head. He took a pair of metal nippers and sterilized them in a flame thoroughly. Then nipped the necks of these little vessels off, let air go in, then took the flame and immediately sealed it again, and then waited to see if it would produce bacteria. He did that to a few of them there. He then climbed Mount Poupée in the Jura Mountains. He then went to Chamonix in the Alps and hired a guide and a mule, and they went up the Mer de Glace on Mont Blanc, and he got up as high as he could and did it again. Well, the vessels that had been opened on the slopes of Mont Blanc produced practically no evidence of bacterial activity. The ones on Mont Poupée, which was much lower, showed much more. And the ones that he opened down in the field where there was biological activity all around, practically all became infected. So he felt he had demonstrated that this was bacteria in the air that was simply getting in there and doing the contamination. Pouchet said, no, it's the oxygen that does it. As it was known by then, the French had invented what we call today canning, because if you seal something up and then boil it, you can preserve food. But Pouchet said that's just because there's no oxygen gets in. Just if oxygen goes in there, it'll start to produce bacteria. So he went down to the Pyrenees. He hired a guide and a mule, and he went up on a glacier, and he did the whole experiment over again, and when he came back, all of his vials became contaminated. He said, you see, it's because oxygen got in there. The pastor said, did you sterilize your metal nippers? He did not sterilize his metal nippers, and that, of course, was the explanation. Well, this all came to a head, I think it was in 1864. Anyway, it was the great lecture that Pasteur gave at the Sorbonne. It was on April 7th, I know, and he slaughtered Pouchet. And it is an interesting sidelight on the history of science that today, if there was a lecture of this sort on a frontline controversy like that between, say, Gell-Mann and Jeff Chu on the explanation for the multitude of elementary particles, is it Jeff Chu's bootstrap principle or Gell-Mann's eightfold way? Well, nobody can understand their arguments except other physical theorists. But in those days, things were simple enough, so the people in the audience that evening at the Sorbonne included Georges Sand, the poetess, Alexandre Dumas, the inventor of the Three Musketeers, sculptors, musicians, artists, aristocrats, the elite of Paris came there to hear Pasteur do his stuff. Well, his arguments were not only making fun of von Helmont, because he was the one who told that story about the mice, but also on a very sophisticated chemical level. He pointed out that the proteins, the synthesis of proteins outside a living organism today would be impossible. Of course, it's possible now with fancy chemical techniques, manipulation, but in an oxidizing atmosphere such as we have, the amino acids that hook together to form the proteins just couldn't do it. It was a very convincing argument. It was a correct argument in terms of what was known then, and it was not until the late 20s and the early 30s of this century that Oparin in the Soviet Union, Haldane in England, saw the answer. And the answer was simply that the world, for most of its history, in fact, has been very different from what it is today, chemically speaking. It had an atmosphere that was essentially hydrogen-dominated. We still had all that hydrogen. It hadn't all gotten away. And whenever a little old oxygen molecule came along, two hydrogen molecules grabbed it and made it into a water molecule. Two hydrogen atoms grabbed it and made it into a water molecule. And the result was that there was very little free oxygen around, no rust, no fire, no cigarette smoking, no oxidation, no combustion. So the chemistry was very different. And One of the students of Harold Urey at the University of Chicago in 1953, and that seems very recent to me, Stanley Miller, decided to see what would happen if you took this hypothetical atmosphere of the Earth, made up the way the atmosphere is today, but with the hydrogen combinations instead of the oxygen combinations, so that you had methane, ammonia, water, and hydrogen as the basic components of the atmosphere. And he made up a mixture of this sort and put it in a system of glass vessels, and one of them was a retort that he put over a little flame to keep the water burbling and make the vapor circulate through the system. And then he put in an electric sparker, because he knew that if you're going to have these very simple gases, which are really just the combinations of hydrogen with oxygen, carbon, and nitrogen, that make them synthesize into more complicated things, you have to put in energy. Now, there's plenty of energy available on the primitive Earth, because you had this searing flux of ultraviolet radiation from the sun in those days before we had oxygen, free oxygen to combine three oxygen molecules to make ozone, which absorbs the ultraviolet and makes the world habitable, and will continue to do so unless the SSTs break it all up. He had the ultraviolet, but he couldn't use it in the laboratory. It was just too difficult, so he used sparks instead. You had lightning, of course, anyway on the instrument, but he just had this little sparker going away in there, 70,000 volts going in there. And he got the system going. He looked carefully, saw that the water was clear, bubbling away in his retort. The gases, of course, were all invisible, clear gases. He went home. When he came back the next day, the water had turned pink. He let it burble away all week. At the end of the week, the water was deep red. He opened it up, analyzed it, and discovered that indeed this mixture contained a whole array of organic molecules, including glycine, alanine, two of the basic amino acids, formic acid, and so on and so forth. Well, this initiated an enormous surge of research into this process of chemical evolution. Darwin, after seeing the nature of biological evolution, looked back beyond the first living organism and speculated that there must have been a preceding phase of chemical evolution whereby the simple chemicals evolved into more complex ones that finally organized themselves into something that could be called a living cell. Well, since the Miller experiment, people have been watching, experimenting to see how this process runs in this producing atmosphere environment. For example, out of the Ames Research Center of NASA on the West Coast, a few years ago they decided that they thought at least that they had synthesized adenosine triphosphate, ATP. ATP is the energy currency of life. One of the most important chemicals to the life process, because it transports energy to where it's needed in the living organism. And this is true of every living thing on Earth, whether it's an amoeba reaching out to grab a little bit of food, or Van Cliburn playing the scherzo from a Tchaikovsky piano concerto. The energy comes from ATP, a dramatic testimony to our common ancestry. All life on Earth, there's only one form of life on Earth, chemically speaking. And these people felt that they had ATP that had synthesized itself there in the laboratory, but while it can be analyzed in various ways, the simple way to do it is to just drop it on a firefly tail. Because the way a firefly makes its tail glow is to just squirt a little ATP in there. But Ames is out in San Francisco Bay, and there are very few fireflies, if any, around San Francisco Bay. But they found an outfit in Mount Vernon, New York, that specializes in all kinds of biological oddities, and among other things, they had frozen firefly tails. So they ordered 2 gross of frozen firefly tails, air freighted to California, sprinkle their mixture on it, and the tails flow beautifully. Well, there's been, as this research has gone on, there have been people who've been troubled by the idea of men in white coats trying to do this act of creation, so to speak, in the laboratory that perhaps was a sacrilegious thing, or there was something a little bothersome about it. And George Wald at Harvard has addressed himself to this, I think, in a very interesting way. He says, that these people in the laboratory are not going to synthesize life. What they're trying to do is to find out how life has synthesized itself. Because it appears now that life is built into the chemistry of the universe. Just as gravity is built into the physics of the universe, so life is always there, standing in the wings, ready to appear when the right conditions are laid in front of it. And all these people in the laboratory are trying to do is to understand those conditions, set them up in the laboratory, and stand back and watch life create itself. But with this understanding of the life process, of the evolution of life, we then look out and have a feeling that life probably has originated on a great many of those Earth-like planets. We certainly have no way to estimate how many, because the critical question has still not been answered. Having evolved all of these chemicals, enough of them to get this little machine going, to set up a unit with a membrane around it that can take in food from the environment, that can reject waste materials back into the environment, that can reproduce itself, replicate itself from generation to generation, and keep the machine, make little models of itself. How you go from the soup of these chemicals to this organized little unit, that we still don't know. We still don't know how often that occurs. But we know it's occurred once, and it's reasonable to assume that it's occurred a certain number of other times. Well, assuming then that there's at least a very small percentage of these billion or so planets in the Milky Way galaxy that have gone through this and produced life, estimates run much higher, some lower, but let's say 1 million of them have. What percentage of these then will have produced intelligent life? We certainly see on Earth dramatic evidence of the way in which, once that spark is lighted, life presses itself into every ecological niche. Every way that life can find to make a living, so to speak, it does so. If there's a way to live in the sea, or on the land, or in some little nook or cranny, some little creature will evolve to fill that nook. And this produces a very striking phenomenon, a form of parallelism in evolution, whereby if there are certain ways of life, different organisms may evolve along completely independent routes to take advantage of that particular way of life. One of the most neat to me is the evolution of wings, because there's a way of life in the sky, and therefore wings have evolved over and over again. Now, they've never evolved on Mars, because the atmosphere of Mars is so thin that you could not have flight on Mars. In fact, in planning our landing of a Viking spacecraft on Mars, one of the great problems is to try to get the darn thing down without smashing it to bits, because the air is so thin. But on Earth, there obviously is a way of life in the sky. And so there were reptiles that flew during the age of the dinosaurs, pterodactyls and so forth. There are, of course, we'll probably see some fish flying before we're through this trip. There are countless insects that fly, birds who evolved from the reptiles but by an independent route. There are mammals who fly, the bats, and so on. And the wings of these creatures have many features in common, not because of common ancestry. They have no common ancestry in that sense. Their wings are similar because of the laws of aerodynamics that specify what is a successful wing. And one of the strongest factors for survival, a great advantage for survival, obviously, because it's meant the survival of that species over and above all others on Earth is intelligence. Maybe in the end, intelligence will be our nemesis, but at least so far it has had great survival value, and it's reasonable to suppose that it will evolve on along other paths of evolution. And it comes up rather early in the game when you come down to think of it. If any of you have had any experience of no-see-ums or mosquitoes or any of those tiny, insidious, fighting creatures, they're hideously smart. You know, just as you're about to swat them, they know, they take off, they evade. They're extraordinary. Now, obviously, this is built into a very simple computer system, but think how tiny that little brain is. What a primitive step along the road to the evolution of intelligence. And yet, even at that early stage, there was that much intelligence. Well, assuming then that there are a certain number of planets that have life that's intelligent, and that therefore becomes technological, how are we to communicate with them? Well, none of them will be where we are today, because the rate of growth of change is so extraordinarily rapid that we cannot expect to ever see anybody who's at this stage, because this is just a moment in time, a tick of the top, a tick of the clock in the evolution of a technological society. When you think that only 10 or 15 years ago, we were incapable of transmitting signals over interstellar distances, and we now only have a limited capability in that direction. Hopefully someday we'll have much more energy at our disposal. So nobody else is where we are. They're either behind us or ahead of us. And so the only people we can be interested in and have any hope of communicating with are those who are ahead of us. And therefore we must assume that the people we're looking for are ahead of us and try to guess how they might manifest themselves, how they might call us, and so forth. And this was a game that began about 10 years ago. Actually it began in '59 with the discussion of, 14 years ago, time flies, with the discussion of what might be the uniquely rational channel of communication. Now, there are two great problems in this area. One is where to look, and the other is how to look. Where to look is easy to understand. All you have to do is to look on the games deck and look at the sky on a clear night. You're only looking at a little under half of that problem, because of course you're looking at half of the celestial sphere. That enormous panoply of stars, where do you point your transmitter or your receiving antenna? So that's one problem. And your pointing has to be pretty accurate if you're going to pick up that faint signal that's gone many, many light years across vast interstellar distances. The other problem is very similar, but it refers to the radio spectrum, or to easy as can be to tune by it and never even hear it unless you're tuning terribly carefully. And you just multiply that many thousand-fold in terms of a signal that's being transmitted over these enormous distances, and you have that. Where to look? Well, in '59, Ciccone and Morrison at MIT, and almost at the same time Frank Drake, down at the National Radio Astronomy Observatory, both realized that there seemed to be a uniquely logical channel. You know, it's like your Aunt Martha coming in from Los Angeles to New York, if you live in New York. You know she's arriving tomorrow, and you suddenly realize that you forgot to tell her where you live. You don't know what plane she's coming in on, or even what airport she's coming in at, and the problem is, how do you meet her? Is there some uniquely logical rendezvous place to go to? The top of the Grand Central Building, the Empire State Building. Well, it's not the tallest anymore. Maybe it's the World Trade Center. Maybe it's the information booth at Grand Central, except she isn't coming in by train. Maybe it's Cousin Minnie's apartment in Queens. Maybe she'll think of that. Is there some place they would think of, she would think of, in the case of the communications with this super civilization, that they would think that we would look at? At that conference in Burikan a year ago last fall, one of the Russian scientists said, you know, we're playing a game, a sort of a cryptographic game, in which the goal of the game is not to deceive the other person, but to see if you can make him win. If you can set up the rules so that he wins the game, so that he can decipher what you're saying, so he can find you. Well, with the Milky Way, there's so many dust clouds and obscurations that we only see a very small fraction of it. The hydrogen clouds whisper to us through that dust, and we can reconstruct the whole structure of the galaxy by looking out at this magic wavelength of 21 centimeters. Obviously, that was the landmark they thought. And so they initiated Project Ozma at the National Radio Astronomy Observatory in Green Bank. And on a memorable day, on I think it was April 8, 1960, the 85-foot dish of the observatory was turned towards Tau Ceti. For the first time in human history, man, in a rational, scientific way, tried to intercept signals from another world. They picked Tau Ceti and another star, Epsilon Eridani, because they were the two stars similar to the Sun, reasonably similar to the Sun, that were single stars and closest to the Earth. And they followed Tau Ceti with this beautiful motor-driven dish all day until it set behind the West Virginia mountains, and then they swung over to track Epsilon Eridani. And before, as soon as they locked down the star, and before they could even turn up the audio system, the needles all began to go off scale and beat. As soon as they turned up the loudspeakers, they could hear this signal coming in. Strong, rhythmic, unmistakable. Well, Frank Drake, who was running the experiment, knew, of course, that if he reported this, it would be a sensation. He could not believe that this was the real thing. The chances of having hit it first try seemed very small. He sent one of his men to the men's room to see if there was somebody using an electric razor. He figured there must be some kind of electric interference getting into the system. And then he said, all right, the real test will be to train that antenna just a little off the star. If that signal is coming to us from Epsilon Eridani, if we train off the star, it'll cut it off like a switch. So his men went to the controls, and just as they reached out, the signal stopped of its own accord. So he swore them to secrecy. Night after night, he trained on that star, and finally, they heard it again. This time, they did that critical test. It swung off the star, and the signal was just as strong a little to one side of the star as it was right on the star itself. So they knew it was something closer than that. And they began to, that star, incidentally, is a little over 10 light years away. That is, it would take any signal from it 10 years to get to us, whether it was radio, light, or anything else. Well, they then discovered the people of the Naval Research Laboratory, who knew they'd been doing this and been doing some 21 centimeter work themselves, said rather slyly on the phone the next day, Frank, have you been hearing anything on 21 centimeters? Frank said, well, as a matter of fact, we have. Well, anyway, to make a long story short, it did turn out to be intelligent life of a sort, namely the U.S. Air Force. It was a radar jamming experiment in which they had an airplane loaded with radar jamming equipment. And every now and then this plane would get near enough the antenna beam so they get the signal down the beam. And that's what they were picking up. But people haven't given up. 2 years ago, in 1971, Troitsky in the Soviet Union carried out a very similar experiment. He looked at 21 stars, 21 of the nearer stars. He used a somewhat lower frequency, 927 megacycles as opposed to the 1420 of 21 centimeters, but it was a negative experiment. And then last year, one of our shipmates, no less, Dr. Verschuer at Green Bank again did the Ozma-type experiment, only this time he used a much bigger antenna, one of the newer ones, two of the newer ones, the 300-foot dish, an enormous dish. Imagine 300 feet movable dish. It can only move in the meridional axis, and meridional direction rather. But he used that. He used a 140-foot dish that can track the star all the way across the sky. He looked at 10 stars, including Barnard's star, our old waltzing friend that wiggles across the sky. Another one that has similar evidence of a planetary companion, and Tau Ceti and Epsilon Eridani, and negative result again. Well, of course, these looks only last an hour or so, and they involve only the nearest stars. Practically nobody believes that the nearest 10 or 20 or 30 or 50 or even 100 stars is likely to be the one. But this has made people wonder, well, now, what really is the logical way to go about this job? How would they try to communicate with us, or would they try to communicate with us at all? Would they be interested in it? Would they be interested particularly in a civilization that is so far behind them, obviously, technologically? Well, Freeman Dyson at the Institute for Advanced Study at Princeton, brilliant English theorist who was brought there by Oppenheimer some years ago, has speculated he sort of carried Malthus to reductio ad absurdum, so to speak. He says the Malthusian idea that population always outstrips the food supply will force a highly technological civilization that still can't control its population to take its planets all apart and make new planets that are hollow and that provide much more room. And I don't know how you'd stay on such a planet. You'd have to have magnetic shoes because the gravitational field would be so weak. But anyway, he's got a system of so many planets going around this particular star that you no longer can see the star. All you would be able to see in such a system would be the infrared radiation from the waste heat coming off from the outsides of these stars facing the cosmos. So he suggested that we look for these infrared objects, and they found some rather strange infrared objects in the last few years, but it seems very unlikely that they are Dyson civilizations. And they call them Dyson civilizations now, and the Russians, particularly Shklovsky, who has just been elected a foreign member of the National Academy of Sciences in Washington, Shklovsky has proposed a Dyson civilization. If it had that much technology and had all the energy of its star available, would build a beacon that we ought to be able to see, and perhaps we ought to look at one of the other galaxies to see if it's that bright a beacon. A few years ago, there was a great deal of excitement at Cambridge University in England when the British were doing some very high-speed recording of the quasars, some of these very distant brilliant objects. And a girl there began to pick up some very rhythmic signals that were unlike anything in nature. These pulses came in at rates of a half a second up to a second apart. They were like clockwork. In fact, they were so rhythmic, so precise, they were like a cesium clock. And when they first reported this at the Institute for for Space Studies in New York, I was in the audience, and I remember noticing that the slides that they showed labeled these four objects LGM1, LGM2, LGM3, and LGM4. Well, those of you who saw that movie the other night about the violent universe know what LGM stood for. It stood for Little Green Men, because the only rational explanation early on seemed to be that these were artificial signals. In fact, Frank Drake, for example, speculated that they might be navigational signals, because we use highly rhythmic signals as a way of navigating. This is essentially the nature of the Loran system that this and many other ships navigate by, and he thought this was a navigation system for interstellar travel. But of course today, these are the pulsars. We know that there are a great many of them. They are highly condensed objects rotating very rapidly. I think we're in for a great many more of these, so to speak, false starts. Ronald Bracewell at Stanford University, professor at Stanford, radio astronomy, has proposed that radio really isn't the logical way to try to communicate with another civilization. There are so many candidate stars, you really don't know who to aim your signal at, and it would be more economical to send a messenger. Not Scott Carpenter or Neil Armstrong, but an automated messenger. We are already getting to the point where we can build computers with almost human capabilities, and certainly one of these super civilizations could produce a computer that was very comparable to a human brain. It could be mass-produced and stuck in these devices and sent off to go into orbit around 1,000 or more nearby stars, and simply sit there orbiting the star, keeping quiet until it hears narrowband radio transmissions and other evidences that a technological civilization is beginning to whimper somewhere in the area, and then begin to talk to it. And Bracewell pointed out that Sturmer, a Norwegian, a man who did very advanced research on the aurora, on the Earth's magnetic field and so forth, reported a number of peculiar echoes. He didn't hear them himself. He heard these from other experimenters, but early in the work with radio, early in this century, and I guess the 30s actually, they heard these peculiar echoes coming back from their radio transmissions. They didn't come back at any uniform rate. Some of them could have been echoed off the moon. Sturmer thought perhaps there were ionized clouds of gas out there in interplanetary space that were sending these echoes back. But Bracewell proposed that, this is the kind of thing we should be on the lookout for, that this might be a messenger in the solar system trying to tell us where it came from. Well, just in the last few months, the Journal of the British Interplanetary Society has published an article by somebody who thinks he's deciphered those signals that came in back in the 30s. I think it's from Alpha Boötis or something like that. It's a messenger saying, I have come from Alpha Boötis, and so on and so forth. Well, it seems very far-fetched to me, because he's going on a very meager bit of information. But that was Bracewell's idea. There have been other thoughts, but one of the predominant lines of thinking now is that eavesdropping is probably going to be the answer. That we cannot be sure anybody's trying to call us, and if there are civilizations around that are much more advanced than ours, we're already making an awful lot of noise in the radio spectrum. We've got these TV stations that send out a signal like a great sheet that goes out over the surface of the Earth, but then goes right out into space. And as the Earth rotates, each one of those is like a lighthouse beacon sweeping the whole celestial sphere. We've got our BMUs, anti-ballistic missile antennas, putting very powerful pulses out across the Arctic Ocean, looking for crystals coming off the surface of the Soviet Union. Just to tell you one other thing about Bracewell's hypothesis, which is sort of fun, he proposed that perhaps one of these civilizations would not send a messenger of that sort, but simply a relayer. When it heard signals coming from within its planetary system, it would relay them back. And if in that case, this was say 25 or 30, 40 years away, the star, which is about as close as you would expect it to be, those signals would just be getting from Earth. They'd be hearing Kate Smith singing God Bless America, and Raymond Graham Swing doing his broadcasts about the invasion of the lowlands. Some have even said at that point they'd probably switch the dials and say that particular civilization is done for, let's look somewhere else. Well, last year NASA had Stanford and Ames Research Center do a study of the kind of antenna system that you need to be reasonably sure of intercepting this kind of information from some other civilization to detect its presence. This was Project Cyclops, the one eye that the world would have looking out into space, and it was run by Barnard Oliver, Vice President for Research of Hewlett-Packard, the leading electronics, highly sophisticated instrumentation firm on the West Coast, a very sophisticated and hard-headed fellow, or reasonably hard-headed. They came up with a scheme for a field of antennas, dishes, each 330 feet, 100 meters, 330 feet in diameter, starting out with a few and building it up until you had thousands of these 300-foot antennas spread over a great area of perhaps many square miles, all capable of being aimed at a single point in the sky. Their input, their received signals processed by computer, and so forth and so on. It would only cost about $10 billion spread over 10 or 20 years. Well, obviously Congress is not very likely to approve such a thing today, but nevertheless, their theory was, their idea was that this could be done in small steps. The first steps, the first few dishes produced exciting scientific information. They could increasing the array until they had it big enough to really have some point in really going all out. But the only other hypothesis that I'd like to mention is that of John Ball of Harvard College Observatory, which is the zoo hypothesis. The zoo hypothesis is simply that no advanced civilization would really be interested in people like us in terms of communication, but we would be enormously interesting from a curiosity point of view, and that perhaps we have already been declared a wilderness area, that nobody is to interfere with us, and nobody is to make a noise that might disclose their presence to us. Well, that's all pretty far-fetched. But Bernie Oliver has summed up what many others have said earlier in this discussion, which is that if we did make contact, if, as Bracewell proposed many years ago, these civilizations have been in contact with each other for 4 or 5 billion years, as in fact Oliver proposes in one of the current issues of the Bulletin of the Astronomical Society of the Pacific, then they have built up a fantastic heritage of knowledge about the history of the galaxy. He writes that such a heritage exists, then interstellar communication would provide not only an exciting future for the human race, but access to the remote past as well. For example, pictures of the Milky Way, Messier 31, and the universe, taken over a span of 5 billion years, would be of enormous interest to cosmologists. The geobiological histories of countless planets would reveal the complete story of life in our galaxy to the present time. But more intriguing would be the information whose nature we cannot even imagine at our present state of evolution. Well, it's a pretty heady thought. Thank you very much.